Hi everybody, Mrs. Pesek here. We are looking at section 3.9, curve fitting with polynomial models. And some of this is going to be a review for you. To create a mathematical model for a set of data, you need to determine what type of function is most appropriate. So recall, we have used finite differences. Little typo there. Finite differences can be used to identify the degree of any polynomial data. So if you recall, if we have a set of data like this, we can determine if the x's are evenly spaced. Let's check, are the x's evenly spaced? Yeah, they're going up by 1 each time. So if they were going up by 1 each time or 2 each time or something like that, they would be evenly spaced x values. Then we can determine the best fit for this. Should it be a quadratic? Did this data come from a cubic or a quadratic or a quartic? And we can do that by taking finite differences. So let's do that now. So if we take negative 10 minus a negative 4, that's negative 10 plus 4 is a negative 6. Negative 4 minus 6 would be a negative 10. 6 minus 14 is a negative 8. 14 minus 14 is 0. 14 minus 0 is 14. This is your first order differences. Are they equal to each other? No. So that means this data is not linear. It's not a degree 1 data. What about the second order differences? Negative 6 minus a negative 10 would be negative 6 plus 10, which is 4. Negative 10 minus a negative 8 would be negative 10 plus 8, which is a negative 2. Negative 8 minus 0 is a negative 8, and 0 minus 14 is a negative 14. This is your second order differences. They are not equal to each other. So let's move on. And we know this data right here, all of this did not come from a degree 2. So it's not quadratic. It will not fit a parabola. Let's try third degree order third degree finite differences. If we take 4 minus a negative 2, that's going to be 6. And negative 2 minus a negative 8 is negative 2 plus 8, which is 6. And negative 8 minus 14 is negative 8 plus 14 is also 6. So the third order differences are all the same non-zero number. All right. If they're all the same non-zero number, that means that we have that this data is cubic. It's a degree 3 data. Because the third order differences are equal, that means the data can be modeled by a polynomial function of degree 3, which is a cubic function. All right, just a little recall here, finite differences of polynomials. If the function is linear, that would be degree 1, and the finite differences that would be constant would be the first order differences. If it's quadratic, that's degree 2, and the second order differences would be equal. If it's cubic, that's degree 3, then the third order differences would be equal. I think that was supposed to say, oh, I got that locked. I think this is supposed to say third. My apologies. If it's quartic, that's degree 4, the fourth order differences would be equal. And if it was quintic, that's degree 5, the fifth order differences would be equal. All right, let's take a look at this notes must do. You're going to use finite differences to determine the degree of the polynomial that best describes the data. So here's the table. X, first of all, are they evenly spaced x's? Yes, it looks like they keep going up by 3 each time, so they're evenly spaced. So I want you to, in your notes, do the first order differences, see if they're equal to each other. If they're not, go on to the second, and so on, like we did in that last example. All right, so please pause this video to take the first order, second order, whatever you need, and then state this data is quadratic, or this data is cubic, or this data is quartic. All right, and when you're ready, resume this video. Okay, you do not need to copy this down, but if you are doing finite differences on real life data, you may not get the finite differences to all be the same non-zero number. As long as one finite difference row has all very close numbers, then you can choose to write a polynomial model that you would have had the data given you exact finite differences. In other words, as long as the finite differences are close, then it's okay. Let's take a look at this example. The table below shows the population of a city from 1960 to 2000. Write a polynomial function for the data. So in 1960, the population was 4,267,000, which means it's really 4,267,000. In 1970, it was 5,185,000, right? Because the population is in thousands here. So if we take the finite differences, and I got my little calculator here to help me out with this. If we take the finite differences here,
Mr. Welch, please call extension 1100.
And we take 10,812 minus 7,830, I'm getting 2,982. And then for the next one, that's 7830 minus 6,166. I'm getting 1,644. And then if I take the next one, that's 6,166 minus 5,185. I'm getting 981. These don't look so close. Let's do this last one and then try moving on to the second order differences. 5,185 minus 4,267, I'm getting 918. These are not very close, so I don't think the first order differences are close enough to say, oh, this data can be modeled by a linear function. So let's go on to the second order differences. With the second order differences, if I take 2,982 minus 1,664, I'm getting 1,318. And with the next one, 1,664 minus 981, getting 683. That doesn't seem very close. And if I take 981 minus 918, I'm getting 63. That's not so close. So I don't think this data can be modeled by a quadratic function. So let's move on to try the third order differences. And I know I don't have very much data to work with, so I only have two subtractions to do. If I do 1,318 minus 683, I'm getting 635. And if I take 683 minus 63, I'm getting 620. Now that's pretty close. If that's close, and this came from the, that's close, so third order differences, that means that we have, this data is going to be coming from cubic, all right? So let's talk about how to get the actual data for this. So if we go to our graphing calculator and we go to a lists and spreadsheet page and we are putting in year and population. So I'm going to type in year, and I want you to do this on your calculator also. I'm going to ask you to show me this with your notes. So we're going to get year, population. Let's see, for 1960, let's just call that year 0. So we'll make all the years from 1960. So it's going to be 0, 10, 20, 30, and 40. All right, and then we go over here and we have 4,267, 5,185, 6,166, 7,830, and 10,812. All right, and at this point, we are going to find the we're going to do cubic regression on this. So we're going to go to add a page, and we're going to go to a data and statistics page. Here's our data, but it's not organized yet. So I'm going to click down here and select year. and I'm going to click over here and select population. So there's my data, and we think it's going to be modeled nicely by a cubic. So we are going to do menu, analyze, regression, and then show cubic. There it is. That's our cubic equation. And the nice thing that we can do, we can actually get this and test out, like, what would you predict? Let's say the follow-up question to this problem is predict the data in the year 2010. All right, so what you can do is you can add a calculator page. So let's go to menu, control doc, add a calculator page. And right here, before we type anything in, we push menu again. We're on a calculator page, push menu, and go to statistics, stat calculations, and we want to choose our X list, which is year, and we want to choose our Y list was population, and we want to save it to some function. So we're going to save the regression equation to F1, say OK. And notice that it is now available to us if we go Control Doc, add a graphs page now. If I do an up click, there's my function. I push enter and it should be graphed. I'm not seeing it though, so I can do menu, maybe menu, window zoom, zoom out. Where is that? It's pretty high function, I think. Yeah, as a matter of fact, let's do, skip out of this. Menu, window zoom, window settings. I know that my year goes from 0 to, I believe, like 40 or 50. And my minimum would be, population would be like 0. Well, actually, let's go to see our data. Our data went from like 4,000 up to 10,000. So I'll just say my minimum Y is like 4,000, and I'll say my maximum is like, I'll say 15,000. And there's our data. It doesn't look very cubic because I guess I'm only looking at one piece of the graph. But from here, if I wanted to predict the data for like the year 2010, I could do menu, trace, graph trace, and then type in like 50 would be for the year 2010. So it looks like it's 1.13 E plus 4, so that looks to me, I just lost it, let's see, 50. So it would be 11,300, I believe, would be our prediction for the year 2010. 2010, 11,300, something like that. All right, so that gives you an idea of how to do the different regressions on your calculator. And let's see. So I'm going to stop this video at this time. And I hope you've taken some good notes. Make sure you do the notes must do and that you have this example on your calculator to show me. All right, and write down, let's just say, just write down one good question that you have. All right, and we will see you next time.